Dopant and defect distribution in ultra-shallow junction device study by the Computational Micro-Electronics Method Advanced Kinetic Monte Carlo. Ion implantation has become the standard process to introduce dopant profiles in CMOS technology. One of the major challenges for ion implantation is the fabrication of ultra-shallow source drain structures. In this process, extra interstitials and vacancies are created, which are removed from the device with a subsequent annealing. These annealings cause transient enhanced diffusion, which leads to the widening of the implanted profiles. A full understanding of the implant process and subsequent annealing is needed for process simulators to correctly account for transient enhanced diffusion. A simple device structure was made to study the defect formation during implantation and diffusion process. Now let's implant arsenic. Arsenic of 3E15 dose was implanted with 20 kilo electron-volt energy at a tilt angle of 7 degrees. Here's the profile after implantation. Now let's have a look at the implantation process stepwise. During implantation, each individual ion produces many point defects in the target crystal on impact, such as vacancies and interstitials. Vacancies are crystal lattice points unoccupied by an atom. In this case, the ion collides with a target atom, resulting in transfer of a significant amount of energy to the target atom such that it leaves its crystal site. This target atom then itself becomes a projectile in the solid, and can cause successive collision events. Interstitials result when such atoms or the original ion itself come to rest in the solid, but find no vacant space in the lattice to reside. We can observe vacancies are concentrated more towards the surface, unlike the interstitials, which are concentrated in the lower areas away from the surface. Ion implantation causes damage to the crystal structure of the target, which is often unwanted, so ion implantation processing is often followed by a thermal annealing. So now let's anneal the device at 950 degrees Celsius and see what happens. We can observe the 311 defects in less than 1 second. 311 defects are extended, rod-like defects that play a central role in the processing of SI during integrated circuit manufacturing. The evolution of ion implantation-induced damage in silicon can be very different during the subsequent annealing step, depending on whether or not amorphization is reached. In cases where damage is not sufficient to amorphize the lattice, damage can evolve into extended defects, like the 311 defects, dislocation loops and voids through the agglomeration of point defects. 311 defects followed one of two possible evolutionary pathways as annealing times progressed, unfolding to form dislocation loops or dissolving and releasing interstitials. Results indicate that in this temperature regime, 311 defects are the preferential site for dislocation loop nucleation. We can observe the number of 311 defects are decreasing, and there is formation of a loop in the place of a previous 311 defect. By continuing the annealing, we are able to remove few dislocation loops, but not all of them. Few dislocation loops grow in size during the continued annealing process. So the loop we were looking at is among the loops which got removed due to annealing process. Atomistic AMC is a very effective tool for accurate modeling of diffusion and defect formation during ion implantation. AMC approach is a fully operational front-end process simulator stage, particularly efficient and realistic under extreme conditions such as deep submicron dimensions. AMC can be used in the design of devices and the optimization of junction formation to improve device performance.